Greetings and welcome to the Dr. J Vlog series. It's Monday, September 8th, 2025, and on Mondays we talk about mathematics and statistics. But being September 8th, quick shout out to JP who turns 32 today. Happy birthday, JP. And today we're talking about flowers and specifically about the Fibonacci sequence. So 32 isn't quite in that sequence, but that's okay. I'll explain more in a moment. In general, nearly everyone can appreciate the beautiful gardens that exist in our local communities. Who among us doesn't appreciate the serenity of green spaces that often include the vibrant colors of the blooming flowers, the branching of trees, sometimes into these incredible sculptures, or perhaps just the arrangement of seeds in many plants and leaves on the stems that yield such remarkable patterns. As you probably well know then, the human brain has evolved then to recognize patterns in nature, in our immediate environments. But somewhat less well known perhaps are a couple of key mathematical principles that help to describe these patterns. One, of course, being the Fibonacci sequence, and then the related concept of the golden ratio, because these show up repeatedly in nature. So, in short, in addition to the aesthetics involved, we can simultaneously appreciate the utility and the beauty of the mathematics that help us describe the natural world. Okay, so I'm going to change up the view here, a little slide presentation, if you will. All right, so as I said, we're talking about flowers in the Fibonacci sequence. So the Fibonacci sequence deserves special attention because of the elegance of its simplicity, and specifically because of its relationship to flowers and plants and seedlings, and much more. And you already know about the Fibonacci sequence, even if you haven't heard the term previously. And more specifically, the Fibonacci sequence consists of a series of numbers that where each number is the sum of the two preceding numbers. So for example, if you start with 0 and 1 and add them together, of course, you get 1. And then if you add 1 plus 1, you get 2. 1 plus 2 equals 3. 2 plus 3 equals 5, right? 3 plus 5 equals 8, and so on. And so there's a more formal formula that's involved there, right? That is, for any f sub n, that's equal to f n minus 1 plus, that is the sum of, with f n minus 2. And so here are the first 10 in the sequence of the Fibonacci number. So again, we start with 0 and 1. 0 plus 1 equals 1. Then the next two, 1 plus 1 equals 2. Then 1 plus 2 equals 3, and so on. Okay, so that's your first 10 numbers in the formal Fibonacci sequence. And again, even though the absolute first discovery of the sequence remains in some dispute, the sequence was actually named, I've mentioned this previously, after the 12th century mathematician Leonardo of Pisa, who later, in the 19th century, was given the nickname Leonardo Fibonacci, son of the Bonacci clan. And this was to avoid confusion with another famous Leonardo in the same city. So whatever the ultimate origins, we know that in 1202, Leonardo of Pisa, Leonardo Fibonacci, published a mathematical text, Liber Abaci, that could be used by the average tradesperson to help with calculations. And in that book, he introduced what we now refer to as the Fibonacci sequence. At least he introduced it to the Western world. And so in nature, there are many examples of Fibonacci numbers appearing in different sequences. So, okay, now just to be clear, just because a series of numbers can be applied to an object, that doesn't imply that there's necessarily a correlation between the mathematics and the reality, but it certainly feels that way. So for whatever reason, then, the Fibonacci numbers show up often enough in nature to reveal that they reflect some kind of recurring patterns. And so you can commonly spot these by studying the manner in which, for example, various plants and flowers grow, looking at the branching of the trees, the arrangements of the leaves on the stems, the fruitlets of a pineapple, the flowering of an artichoke, the arrangements of a pine cone. All of these reflect patterns in nature and specifically involve Fibonacci numbers. If you look at the spirals of seeds at the center of a sunflower, for example, you'll observe patterns curving left and right. I'll show you in a moment. And if you count the spirals, your numbers are going to total Fibonacci numbers. Okay? And there's more. Okay, so there's a special relationship then between Fibonacci numbers and something called the golden ratio. So the golden ratio describes when a line is divided into two parts, and the longer part, A, divided by the smaller part, B, is equal to the sum of A plus B divided by A. And that number, remarkably, comes out to be equal to about, and I'm rounding to 3 decimal places, 1.618. And it's represented by the Greek letter phi. Okay, so again, here's what it looks like visually. And this is an example of the so-called golden rectangle, right? Such that the two shorter sides equal to A, and the two longer sides are equal to A plus B. Okay? And then the ratio of the longer side to the shorter side ends up being 1.618. Again, this is the golden ratio. But what's fascinating is that if we take two successive Fibonacci numbers in sequence, their ratio is very close to the golden ratio. Okay? And again, comes out to be about 1.618. So here are some examples. Now, again, at the very beginning of the Fibonacci sequence, it doesn't work so well. So you take the numbers 2 and 3, and you look at their ratio, it's 1.5. That is 3 divided by 2. And then look at the next two numbers in the sequence. So that would be 3 and 5. 2 plus 3 equals 5. So the next two numbers are going to be 3 and 5. Their ratio, again, in order in the Fibonacci sequence, comes out to be 1.6 repeating. And then 5 and 8 are the next two numbers. Then 8 and 13. And lo and behold, as we go up, and a little bit further, obviously, look what happens. We start to converge. The series starts to converge around 1.618. So in short, what we see is that the Fibonacci sequence and the golden ratio essentially, at more advanced levels or further along in the sequence, essentially end up being the same. By the way, I tend to round it off to 1.62 for what it's worth. And then I think of the number of games in a Major League Baseball season of being 162. That helps me remember the 1.62. All right. Anyway, and by the way, it's remarkable then how often these numbers come up, and the golden ratio and the Fibonacci sequence. And we see this, and I'll show some examples tomorrow as well, but we see this in art, we see this in architecture, we see this in nature, in flowers, and so many different patterns. In fact, it's such a commonly recurring sequence and pattern of numbers that there's a whole scientific journal that's devoted to Fibonacci numbers. It's literally called the Fibonacci Quarterly, published 4 times per year. And so current research has determined that and found evidence that the Fibonacci numbers and the golden ratio, these basic mathematical principles, appear in a great many patterns and structures in nature. And so I guess the attraction then of the Fibonacci sequence and the golden ratio in gardens is likely a combination of their natural occurrence in the environment and the ability then to create these kind of pleasing, easily recognizable patterns and proportions that evoke such a sense of balance and harmony. In addition, the Fibonacci sequence and the golden ratio are associated metaphysically with growth and abundance, and they're often used cross-culturally to evoke a sense of balance and harmony in nature. And they're also symbolic then of prosperity and success. Okay, incredibly then, the beauty of flowers, carefully arranged and nurtured, often end up following the Fibonacci sequence. If you look at the arrangements of their petals and their seedlings, And the pattern arrangement adds an extra layer of fascination if you think about the world of flora more generally. Many flowers exhibit a petal count that corresponds to Fibonacci numbers. So for example, lilies often have 3 petals. Buttercups have 5. Shasta daisies have 21, and dandelions 34. Other examples include the white Calia lily with 1 petal. The euphorbia has 2 petals. The iris has 3 petals. The larkspur, hibiscus, and the wild rose each have 5 petals. Black-eyed Susans and delphiniums have 8 petals each. And the pyrethrum daisy has 34 petals, and so on. But again, I mentioned earlier sunflowers. So one of the most noticeable manifestation of the Fibonacci sequence in flowers comes about in the spirals of sunflower seed heads. So the seeds of these flowers form spirals that radiate from the center. And so here's a picture that I've included. And the numbers of these spirals, when counted in opposite directions, are often, again, consecutive Fibonacci numbers. The most common arrangements in the sunflowers are 21 and 34 spirals. Some have 34 and 55 and so on, okay? But again, if one observes just the head then of this particular example, and you notice the 2 series of curves, one winds in one direction, one winds in the opposite direction. So the numbers of spirals differ, but again, for most spirals, they have 34 in one direction. For most sunflowers, they have 34 spirals in one direction and 55 in the other. And again, that's straight from the Fibonacci sequence and aligns too with the golden ratio, rounding off once again to 1.618, or like I said, I go to 1.62 myself. Okay, so there are countless additional examples in nature and among flowers and amongst their seedlings. And so this type of mathematical harmony is not only visually appealing, but it actually also serves a practical purpose too for the flowers. That is, the optimal packing of seeds ensures the most efficient use of the space within these flowers and maximizes each flower's or each plant's access to sunlight and their reproductive success. So, nature then obviously has its own beauty, as does the mathematics that helps us to describe nature. And the two intertwine, that is nature and mathematics, in an almost magical and mystical way to produce some of the most beautiful and recurring patterns in nature. So that flower that you're looking at is rooted in mathematics too. And it's not an accident that it looks the way that it does. All right, until next time, may you and yours continue to create peace in your lives, nurture love in your hearts, and dole out hugs in abundance. And I hope to see you tomorrow.